Okay. Time for us to consider something that you probably didn't think you would ever consider. Let's consider logarithms of complex numbers. Sure, why not? To do so, we need a construct. We need to think about what it means to exponentiate a complex number. And it turns out that we exponentiate complex numbers in the same way that we exponentiated real numbers. This is Calc 2 coming back at you. You learned in Calc 2 that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. And we propose to do the same thing when exponentiating a complex number. So in this case, z is complex. Z is 3 or 5 or negative 2 or 4i or 2 plus 3i or negative 5 minus I. Same thing. Same thing. If we're going to propose this, we have to ask ourselves, does this series converge? Does this series converge if z is a complex number? And the way we figure that out is we take a look at what happens to the sum after some number n of this. We take a look at what happens to these residues. So this is what happens when you cut off the series after you truncate it after some number of terms, n is the number of terms. These are the terms that are left over. If the series converges, then the residues go to 0. If this has a limit of 0, then we're great. But we know that this sum is less than or equal to the corresponding sum of the magnitudes of z to the j over j factorial. And this is by triangle inequality. So z is an a plus bi kind of a thing, raising it to the j. And so if we take the absolute value of the sum, it's less than or equal to the sum of the absolute values. And we know, because of Math 222, that this, let me try that again. We know from Math 222 that the e to the x series for real numbers, and this is a real number, converges. So if e to the x converges for real numbers, this has a limit of 0. This has a limit of 0 because if we truncate after a finite number of terms and we let that finite number get bigger and bigger and bigger, the residues have to get closer and closer to 0. These are non-negative numbers that are less than or equal to 0, so this also has a limit of 0. And so this series, this e to the z, converges for all complex numbers, which is so weird to think about. If z is 11 billion minus 11 billion I, still converges. Let us also consider the following. Is it true that e to the z times e to the w is e to the z times w? Is that true? Is it true that e to the z times e to the w is equal to e to the z plus w? Is that true? Well, we can expand the brackets, and if we expand the brackets, we get 1 plus z plus w plus z squared over 2 factorial plus zw plus w squared over 2 factorial, and so on. 1 z plus w. Oh, looky there. Oh, it does work. It does work. So even if z and w are complex numbers, this still holds. And we can prove that by series. That's just so weird to think about. Well, I'll give you one other weird thing to think about. For any complex number, z, which is x plus iy, and that's just the way they normally write it in complex analysis. That's my understanding. That's my understanding of how they write it in complex analysis. We don't write a plus bi, we write x plus iy, with x and y being real numbers. E to the z is equal to e to the x times cosine y plus I sine y. In particular, e to the iy is cosine y plus I sine y. Why? Why is that true? Well, the first part is true because e to the z is e to the x plus iy. That's e to the x times e to the iy. So the fact that e to the z is e to the x times something comes from that. But the question is, can we equate those things? And the answer is yes. E to the iy, well, by 2 slides ago, that's 1 plus iy plus iy squared over 2 factorial plus iy cubed over 3 factorial, and so on. Well, what is that? I cubed is negative I. And what happens? Every other term is real. It has no imaginary part. And you get 1 minus y squared over 2 factorial plus y to the 4th over 4 factorial minus y to the 6th over 6 factorial, and so on. That's cosine of y. That is the Taylor series from Calc 2 for the cosine of y. Then you look at the terms that have an I. There's a y, there's a negative y cubed over 3 factorial, and there's a plus y to the 5th over 5 factorial, and a minus y to the 7th over 7 factorial. And your Calc 2 instructor is going to be very glad that you remembered that that's the sine series. Therefore, e to the iy is the cosine of y plus I times the sine of y as needed. So this is one of those weird things in math where trig comes together with exponentiation, comes together with calculus series. Like there's a whole lot going on all together, and I'm just going to make that a little bit more weird. Notice that z is r e to the I theta. This is how we expressed this is how we expressed complex numbers as polar coordinates. So z is r times e to the I theta, which means that the log of z is, well, that's a product. Logs turn products into sums, right? And the logs are all base e. We don't write natural logs. We don't need to write ln because after you get past Calc 2, every log is a log base e. And so the log of z is the log of r plus I theta. We can find the logarithm of a complex number by finding the log of the r value and then tacking on I theta. Now, granted, you and I both know, because we took Calc 2 and we're familiar with polar coordinates, that there are lots of thetas that represent a particular complex number. Which one do we use? Answer, yes, you use all of them. So what this implies is that the logarithm of a complex number is not well defined. There are many, many numbers that can be the logarithm of a complex number. Sir, if you don't flesh this out, I'm gonna click on a cat video instead. Let's suppose that you want the log of e. Well, the log of e, let's see, that's r e to the I theta, right? I mean, e is e away from the origin. So what are we doing here? Well, the log of e, that's 1. What's theta? Well, theta is 0, or it's 2 pi, or it's 4 pi, and we could go on. Why? Because when we graph e in the complex plane, here's e. So that's at 0, or we swing around 2 pi, or we swing around 4 pi, or we swing around 6 pi, and so on. When we find the log of I, well, let's graph I in the coordinate, but there's I. I is 1 away from the origin. It's 1 away from the origin. Then there's an I theta. So the log of 1, that's 0, plus I theta, where theta is pi over 2, or swing around another 2 pi, or swing around another 2 pi, and so on. You can even take the log of -1. -1's a complex number. You can graph -1 in the complex plane. It's over here. We take the log of its distance from the origin plus I theta. So that's 0 plus I theta, where theta is, that's pi, or swing around another 2 pi, or swing around another 2 pi, or. This is so very weird. So very weird. Anyway, more thing before we go. So let's think about very, very bizarre things. We know by definition that z to the w is the same as e to the w times the log of z, right? When we raise one number to another, we can do it like this. The trick here in algebra 2 is that this is this, and then we use power to a power. So this is our definition on how to raise one number to another number's power. So what if we're trying to do I to the I? Well, if we're trying to figure out what I to the I is, that's e to the I times the log of I. And we figured out on the last slide what that is. We figured out that log of I is 0 plus I theta, where theta is pi over 2 or 5 pi over 2 or 9 pi over 2 and so on. But what's this? Well, I squared is -1. It's just e to the negative theta, where theta is pi over 2 or 5 pi over 2 or and so on. So you can actually get values for I to the I in this way. Which one is it? We don't say that it is any particular one of them. It is all of them. I know, it's really weird. It's really weird. Here's another bizarre thing to think about, shall we? What about that? What about that? Well, that's e to the 4i times log of 1 minus I. Well, how do you find that logarithm? Well, that's the log of the distance that this number is from the origin when it's plotted in the complex plane plus I theta. Well, what's that? That's e to the 4i log root 2 times e to the -4 theta. Well, what's that? E to the log of radical 2 is radical 2, right? Where theta is 1 minus I. 1 minus I is in the fourth quadrant, -pi over 4, or 7 pi over 4, or. So weird. So very weird. But we are allowed to assign values to these numbers in these ways. And we don't worry too much about coming up with the logarithm. There are many numbers that are the logarithm. And so we're okay with multiple answers here. That's probably enough for us to play with for a while. I am glad to let you go back to MCE prep. All the best as you do so. We'll do a little bit of statistics on Thursday and call it a day.